Welcome back to week 10 of the ma161 calculus. My name is Götz Pfeiffer and this video is about graph sketching. In week 2 we found that there are 4 different ways to represent a function. We can describe a function in words, verbally. We can describe a function numerically by a table of values. We can describe it visually as a graph and algebraically by an explicit formula. We've seen that all these four different ways have their uses, have their advantages, and we've also seen that it is possible to transform one such representation into another. From a graph we can read off single values and write them down as a table. From a formula we can compute values and write them down as a table, or other useful transformations. Graph sketching is about transforming a given function into the visual representation. And from all of these, from a verbal description, from a table of values, or from an algebraic formula. If you sketch a graph, decisions need to be made, and which part of the x-axis do you want to use, or in which part of the y-axis, what scale. This essentially boils down what are the interesting features, the interesting points of the graph that the sketch should communicate. To make these decisions, calculus can provide the necessary information. The tests that we just set up provide the information of interest. So far in this course, we've seen lots of graphs that were produced by sophisticated graph sketching algorithms. Under normal circumstances, I would have drawn these by hand on the blackboard. And that's what the graph sketching is about. Not about really sophisticated, precise graphs, but rough and quick sketches by hand. And for this, one can use the following list of 7 guidelines which help to collect the interesting information about a function. And somehow this is like a review of the course so far. Which aspects are of interest, or to support the decisions that need to be made when you sketch a graph. A, you start with the domain. For which x is the function defined? B, intercepts. Where does the graph intersect with the axis? The y-intercept, of course, is the value at 0, and for the x-intercepts one needs to solve y equals f of x for x, which might not always be possible. C, is there any symmetry in the graph? We had this notion of even and odd functions that are symmetric about the y-axis or about the origin, or is the function periodic, like the sine and the cosine function. And this saves work. If you have the symmetry, if a part of the function repeats itself somewhere else, then you don't need to compute these properties again. You can just take the mirror image, or in the case of periodicity, shift things. Asymptotes. We've seen how we can use limits, certain limits, to find vertical or horizontal asymptotes. For vertical asymptotes, we'd find the points A where the one-sided limit of the function to A, there's an f of x missing, and the limit where this limit goes to plus or minus infinity, and that makes a vertical asymptote. For horizontal asymptotes, we would consider the limit to plus or minus infinity of the function itself. Then the information that comes from the derivatives. Where is the function increasing or decreasing? For this we need to find the intervals where the first derivative is negative or positive, and then use the increasing, decreasing test. And f is local extreme values. Find the critical points of the function, the zeros of the first derivative, or where is the points where the first derivative isn't defined, and then use the second or first derivative test to locate the extreme values. And finally, point G here, concavity. Find the intervals where the second derivative is greater or equal, greater 0 or less than 0, and then use the concavity test to find the concavity of the function over certain intervals. And based on this gathered information, one can then decide on a range for x and y. What values of x and y do you need in your sketch to put all these interesting points in? And then one can set up an xy coordinate system accordingly. Then in this system one can throw in the points that have been computed explicitly, the intercepts, the extreme values, and inflection points. And then the curve that one wants to draw passes through these points, rising and falling according to the increasing, decreasing intervals established in point E here, and bending upwards or downwards according to the concavity established as point G here. If additional accuracy is needed, one can always compute more values of f or the derivative. Let's see this in practice. Here's an example. Let's try and use the guidelines to sketch the curve y equals 2x squared over x squared minus 1. We'll go through this program. The domain of this function is all of the real numbers except for those where we divide by 0, so that's all x's different from plus or minus 1. The intercepts, this function is 0, y is 0 exactly when x is 0, so both intercepts are 0 here. Symmetries. You see this, or you check this. This function turns out to be even. It's symmetric about the y-axis, so from now on we can concentrate on the positive side of the graph only, knowing that the negative half will be an exact mirror image of whatever we find. So for the horizontal asymptote, for example, it's sufficient to consider the limit of the function as x goes to plus infinity and apply the usual trick here of dividing both top and bottom function by the highest power of x that occurs in the bottom function, x squared here, and then it becomes obvious that the limit as x goes to infinity of the function is 2, which makes a horizontal asymptote y equals 2. Then at the points that are not in the domain, we see that the limit, the one-sided limits of the function go to plus or minus infinity. That makes vertical asymptotes 1 at x equal to minus 1 and 1 at x equal to 1. Then the next point would be looking at the derivative. And you need the quotient rule to find the derivative of this function, which is minus 4x over x squared minus 1 squared. This is negative, the square in the bottom makes the bottom function always positive, so this is negative when minus 4x is negative. That of course is the case if x is positive. So f is decreasing on the interval from 0 to 1 and the interval from 1 to infinity. Then the derivative is 0 at x equal to 0, so there's a critical point. And by the first derivative test, this is a local maximum. F of 0 evaluates to 0 as a local maximum because of these decreasing and increasing properties of the derivative of the function. Then the second derivative is computed as 12x squared plus 4 divided by x squared minus 1 to the third, and this the 12x squared plus 4 is always positive, and the x squared minus 1 to the power 3 is negative if the absolute value of x is smaller than 1. So that makes the function concave down on the interval between minus 1 and 1, and concave up outside of this interval. There are no inflection points, since the points where the second derivative changes its sign are not contained in the domain. So based on this information, I decide to let my x go from minus 3 to 3. That includes all the important points, that makes room for the vertical asymptotes and a bit outside. And also I let y go from minus 2 to 4, that makes room for the horizontal asymptote and includes the local maximum and a bit room on the outside. So with this decision made, I set up an x-axis here. I subdivide the x-axis into 6 parts, from minus 3 to 3, then the y-axis subdivided into 6 parts from minus 2 to 4, and I throw into the picture the vertical and horizontal asymptotes, the horizontal one at 2 and vertical asymptotes at minus 1 and 1. Then the explicitly calculated points, this time we only have one, the local maximum, f of 0 equal to 0. There's only one known point on the graph, but we know the asymptotes, we know how the function is increasing and decreasing, and how it bends upwards or downwards. And with this information and the fact that it approaches the asymptotes over time, we can complete the graph like this. And this is fun. I do this again. I'll start with the x-axis, labels, y-axis, labels, asymptotes, horizontal and vertical, throw in the points and complete the graph. That's the program. Finish this off with one more example of a slightly different kind. The graph of f of x defined as x times e to the x. Here the domain is all of R, so we definitely need to decide which part of the real number line we want to show. The intercepts, again, f of x is 0 if and only if x is 0, so both intercepts are 0. For the asymptotes, the limit as x goes to infinity of this f of x is infinity, as both factors x and e to the x go to infinity. The limit as x goes to minus infinity here is not so clear. the e to the x approaches 0 as x goes to minus infinity and x goes to minus infinity. There's a competition between the two factors, which goes where, or in other words, this is a case for L'Hopital's rule. If we rewrite this product as a quotient, x divided by e to the minus x, which of course is the same, but then we're looking at an expression where the x goes to minus infinity as x goes to minus infinity, and e to the minus x goes to infinity as x goes to minus infinity. So it's an expression of the form minus infinity over infinity, an indeterminate form where, as indicated at the time, L'Hopital's rule applies, and we can calculate this limit as the limit of the quotient of two functions as the limit of the quotient of the derivatives. Derivative of 1 is 1, of course. Derivative of e to the minus x is minus e to the minus x. And as this minus e to the minus x goes to minus infinity, this inverse goes to 0. So there we have it, a horizontal asymptote, y equals 0. The x-axis is a horizontal asymptote in this case. Then, point E, the derivative, well, we calculated this earlier, this and all the derivatives of the function we computed at some point. It's x plus 1 times e to the x. E to the x is always bigger than 0, so this is bigger than 0 if and only if x plus 1 is bigger than 0. So that determines the interval where this function is increasing and it's decreasing on the rest. Also, this determines the critical point, minus 1, as the 0 of the derivative. And from the second derivative, which is x plus 2 times e to the x, and we can now apply the second derivative test, evaluate the second derivative at minus 1. This is e to the minus 1, which is bigger than 0, so we're looking at a local minimum at minus 1. And the value is minus e to the minus 1, which is approximately minus 0.37. For the concavity, we find that, similar as before, the second derivative is bigger than 0 if and only if x plus 2 is bigger than 0. So from this we know the function is concave down from minus infinity to minus 2 and concave up from minus 2 to infinity. And that makes the minus 2 an inflection point, and the value of the function at this inflection point is minus 2 e to the minus 2, which the pocket calculator tells us is approximately minus 0.27. This accuracy of these values is completely sufficient for the graph sketching purposes. Also, for added, how do you call this, accuracy, I just know that f evaluated at 1 is just e, which is approximately 2.71. So let's throw this in. And then deciding that that x should run from minus 4 to 1 to include all the interesting points, and to let e of x not grow too big, and then correspondingly the y goes from minus 1 to 3 to make room for the local minimum here and the extra value e and 1 that we drew in. We set up an xy coordinate system with these intervals in mind, throw in the points that we've calculated at minus 2, minus 1, 0 and 1, and then using the bendiness, the concavity of the graph and where it's increasing and decreasing. So it's decreasing up to minus 1, it's bending downward up to -2, one can join these dots and get the sketch of the graph. That's how the calculus first and second derivative apply to graph sketching. Next, we're going to use these tools to solve actual real-world optimization problems.